Welcome back to Real Analysis 1. In this video, we are going to talk more about bounded sets. So in particular, I have some vocabulary here, some of which is familiar, some of which you probably anticipated. Then we will state and prove a pretty important result, which I will call criterion for set supremum. Sometimes I call it criterion for sups and infs. Whenever I say criterion for sups, I'm talking about the result that we will prove in this lesson. And we will do some examples and some kind of toy exercises with the idea of having bounded sets. So first, let's just quickly run through this vocabulary. We say that a set A of real numbers is bounded above if there exists some real number B so that B is greater than or equal to A for all A in the set A. So here, little a is an element belonging to the set capital A. Similarly, we say that a set A is bounded below if there exists a real number C such that C is less than or equal to all elements little a, where little a belongs to the set A. So you could be bounded above, you could be bounded below, you could be neither bounded above nor below. If you are both, then you are bounded. So A is bounded if A is bounded above and below. Okay. Then one concept we've seen, in fact, it forms the basis of one of our foundational axioms in our study of real analysis, is this idea of having a set supremum. We say that a real number x is the supremum of A if it's an upper bound of A and it's the least upper bound. So it's less than or equal to all other upper bounds of A. So x equals sup A if x is greater than or equal to A for all elements A in the set A, and if B is also an upper bound, x is less than or equal to B. Okay, so x is the supremum of A if it's an upper bound of A. That's all I'm saying here. It's an upper bound and it's smaller than all other possible upper bounds. We say that x is the infimum of A. Sorry if I'm overusing the letter x here, but new concept down here. A real number x is the infimum of the set A if it is a lower bound and it's bigger than all other lower bounds. So it's like the flip of this definition. We can call it the greatest lower bound as well. So let me write out x is less than or equal to A for all elements A in the set A. It's a lower bound. So x is a lower bound of A, but it's like the biggest lower bound. And if, I'll just keep overusing letters, if B is also a lower bound of A, x is greater than or equal to B. Okay. So we've seen this terminology here before. X is the supremum of A if it's the least upper bound. Here we can say x is the greatest lower bound of A. Okay, so nothing too surprising here. We've talked about being bounded above and having a set supremum. Here we're just going the other direction. You can be bounded below, and you have, if you are bounded below, applying the supremum property, you can establish that all sets which are bounded below have an infimum. In other words, they have a greatest lower bound. Let me now let you write this down, and then we will come back and do some examples actually before we tackle this criterion. Actually, one more thing. I said this word out loud, but I think it's worth writing it down. INF here, this is abbreviating infimum. So the least upper bound is the supremum, and the greatest lower bound is the infimum, and the plural is suprema and infima. So just wanted to establish that vocabulary. Let's take a moment now just to work through 5 examples of sets of real numbers. So for each one, the question is, does it have a supremum? If so, what is it? And likewise, does it have an infimum, a greatest lower bound? And if so, what is it? For each one, I would like for you to pause and come up with the answer on your own and then check if your answer matches mine. So let's take a moment to pause and work out the natural numbers. The natural numbers, of course, are unbounded above, so there is no set supremum, no sup. They are bounded below. Any negative number is a lower bound for the set of natural numbers, as is 0. In this course, we define natural numbers as starting with 1, so 1, 2, 3, 4, 5, etc., etc. 0 is a lower bound, 0.5 is a lower bound, 0.97218 is a lower bound, 1 itself is a lower bound. And that is the greatest lower bound, so it is the infimum of the set. I will write inf of the set of natural numbers. Looks a little weird to me. I'm going to put it in parentheses. What I wrote was fine, but this is also fine. The infimum of the set of natural numbers is the number 1. And there's something special here because 1 belongs to the set. If the infimum belongs to the set itself, that is the definition of the set minimum. So this is a new word for us. The infimum is 1. 1 is a natural number, so it is the minimum of this set. No supremum, infimum is 1, and now we recognize that as the minimum. Take a moment to do A2 now, this interval from 0 to 1. Is there a supremum? Is there an infimum? And now try to answer the questions, is there a maximum? Is there a minimum? For the second example, hopefully you recognize that the supremum is the number 1. That belongs to the set, and that means, new word, it is the set maximum. On the other hand, 0 is the infimum of this set, but it does not belong to the set. So I will write that the infimum of the set A2 is 0, but there is no set minimum. So for the first example, well, there was no supremum, so no maximum. For the second example, the supremum belonged to the set, and therefore there is a set maximum. The maximum is the supremum whenever it belongs to the set. There is an infimum because the set is bounded below. That infimum is 0. That is not an element of the set. There is no minimum. So there is a maximum, there is no minimum. Okay, now try this third set, and I want to say that this set is one that I like a lot. I use this in a lot of examples. I actually call it the Archimedean set, so let me just make a little note right here. That's not standard terminology, but I use this set so often that one semester students were like, we need to name that set, and this is what they came up with, and I really liked it because 1 over n feels like that Archimedean principle. So we will call this the Archimedean set, and take a moment to decide if it has a supremum, an infimum, a maximum, and a minimum. Let's actually take a moment to sketch this set because it is one that we will see a few times at least in this course. So we are looking for reciprocals of natural numbers. The first one that I think of is 1 over 1, so that's 1. And then we have a half, a third, 1/4, 1/5, 6th, 7th, 8th, 9th, etc., 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 etc. So we have all of these natural number reciprocals. They're all positive numbers. So this set is bounded below by 0. So it's definitely bounded below. It has a set infimum. Could the set infimum be larger than 0? So the question is, 0 is a lower bound. Is there a lower bound bigger than 0, which might serve as a set infimum? So could I imagine maybe some sort of positive number like this? And the answer is no, because of the Archimedean principle, the second version that we stated. Any number to the right of 0 is a positive number. By the Archimedean principle, I can fit such a number to the left. So you can always squeeze between 0 and any positive number an element from this set. Therefore, 0 is not only a lower bound, it is the greatest lower bound, and therefore it is the infimum. It's not in the set itself. There's no number of the form 1 over n which equals 0, so there is no minimum. On the other hand, just plain old 1 out here is the maximal element. That might be the easier way to get to the fact that 1 is also the supremum. So, you don't have to think of the sup first. All right, so let me summarize. I think I've been writing sup before inf. So I will write that the sup of this Archimedean set is 1. That belongs to the set. So that is the set maximum. It's the maximal element. The infimum is 0. and that is the more interesting side of this set, but there is no minimum. Okay, take a moment just to work through maybe both of these last two examples. You don't have to be overly rigorous here. Just try to find what you would think the set supremum and infimum would be if they exist. This fourth example is not too exciting. I'm mentioning it because often in analysis, we want to work with small little numbers, and often we give them a form. That form could be 1 over n. So this idea of small reciprocals of natural numbers often gives us a way to kind of slide around on the number line. But sometimes you have small numbers of this form too. These are, of course, also reciprocals of natural numbers, just of a specific style. So 1 over 10 to the k. Another common one to see is like 1 over 2 to the k. Without any supporting justification, I'm just going to go ahead and write down that the sup of this particular set is, of course, the largest member of the set. Actually, it's the set maximum. That's 1/10. So this set does have a maximal element. For very similar reasons to the third example, there is an infimum, but there is no minimum. So the infimum of this set, it's actually a subset of this one, has the same infimum as 0, but there is no min. For this last set, be careful, don't read this too quickly. It's not real numbers whose square is less than 2, it's rational numbers whose square is less than 2. So if we are looking at rational numbers whose square is less than 2, we're essentially looking at rational numbers between negative square root of 2 and square root of 2. Let me just kind of write down the answer. So the supremum of this set is the square root of 2. We've talked about how square roots exist, and this number exists immediately from the Pythagorean theorem. The infimum of this set is negative square root of 2. There is no maximal element, there is no minimal element. Even if I had less than or equal to here, there still wouldn't be a maximal or minimal element because these numbers are not rational. So what I said a minute ago about reading this carefully, if this had been all real numbers whose square is less than or equal to 2, basically it was an entirely different example. Let me say it over here. Then you would have a set maximum and minimum. They would be these numbers, but that's not what we have here, actually for two reasons. So let me just move on from this example. So we have a set supremum, a set infimum. Hopefully these examples were fun and also gave you a good understanding of what a set maximum and minimum is like. Let's now state and prove the criterion for a set supremum. Here's an important result that we will call the criterion for a set supremum. I may also call this just criterion for sups, or even criterion for sups and infs, because you can also convert this statement into a condition about a set infimum for a set which is bounded below, and I encourage you to try to come up with that statement on your own. So what this says is, imagine that you have some element x on the real number line, which is an upper bound for a set A. X is the supremum of A if and only if, for any measurement epsilon greater than 0, x minus epsilon is going to sit to the left of an element from A. Okay, I said that a little bit differently than it's written here, but let me sketch the picture so that you understand exactly what this is saying about the supremum for a set. And as I sketch this picture, one thing I want to point out, in case it hasn't been clear yet, is that when we talk about sets of real numbers, it's important that you don't just picture, say, intervals. We've seen, the Archimedean set, which was a set of discrete points. You could have a set A, which looks like maybe some intervals, some discrete points, whatever. So imagine that A is some kind of collection of real numbers over here. And perhaps the supremum of A is this number here. When I take x and I subtract off epsilon to get x minus epsilon, we are going to take this number here on the real line and scoot to the left. So it's like however big epsilon is, it's some number greater than 0. Imagine that we look at this number x minus epsilon. All this statement is really saying is that if x is the supremum, it must be the case that there's something from A to the right of x minus epsilon, because otherwise this would be a smaller upper bound. So somewhere between x minus epsilon and x, possibly x itself, is an element from A. You have to be able to find something from A over here, because if you could not, then this number smaller than x would be a smaller upper bound for the set A, and therefore x is not the supremum. I basically just did kind of like almost a proof of this out loud, but this is an if and only if proof, so we need to carefully show both directions. This is the idea that I want you to have in mind, though, whenever you think about this criterion, this idea that if you're at the supremum and you slide any amount to the left, you have to have something from A to the right of where you land. Okay, let me step aside, erase this, and then I will come back and we will do this if and only if proof. We will start with the forwards direction, which is very fast. Just going to be a direct proof using the definition of a set supremum. So suppose that x is the sup of A. And let epsilon be greater than 0. Then x minus epsilon is less than x. And therefore, x minus epsilon is not an upper bound of A. There's no need here for contradiction or anything like that. I'm applying the definition of supremum. Since x is the set supremum, it is the least upper bound. A number smaller than x, therefore, is not an upper bound. You don't need to write more than that. So x minus epsilon is not an upper bound of A. Therefore, there must be an element from A which is strictly larger than x minus epsilon. Again, you don't need contradiction here. Everything here comes from definitions. I will do a little bit of contradiction out loud just in case you don't see this right away. If this wasn't the case, if you couldn't find such an A, then you would have A is less than or equal to x minus epsilon for all A in the set A, so for all elements A in the set A. And then this is exactly what it would mean to say that x minus epsilon was an upper bound. Since we know that x minus epsilon is not an upper bound, you can't do this for all A. Therefore, there must exist an A from the set A such that that element A is greater than x minus epsilon. Okay. Again, you don't need to write out this contradiction here. This is a direct proof, and it's using the definition of supremum and the definition of upper bound. The other direction, though, is a little bit trickier. So let's start it, and maybe I'll pause. In fact, that's where I'm going to pause, drawing the backwards arrow. I am going to show the backwards direction by showing the contrapositive. So we want to show that the right-hand side implies the left-hand side by saying that if x is an upper bound which is not the set supremum, then the right-hand side would not be true. Negating the left-hand side is easy. X is not the supremum. Let's take a moment, maybe you can do this to the side and write scrap work, to negate this for all epsilon there exists statement here, because this is always a good exercise in working with logical quantifiers. So just a remark, if I say P if and only if Q, what is not Q? So not this statement. I'm going to write this out very symbolically. If it's not the case that for all epsilon greater than 0, there exists an element little a in the set A such that A is less than, or sorry, A is greater than x minus epsilon. So what is the negation of this statement? If it's not the case that for all epsilon something happens, then that means there exists a special epsilon. I often denote this idea of there's some special epsilon out there that does something with the subscript 0. That's optional, but I like it. There exists an epsilon such that for all A, all elements A in the set A, this does not happen. I got a little turned around. There exists an epsilon such that for all A, it's not this. Okay. such that for all a in A, the element little a is less than or equal to, so not greater than is less than or equal to x minus epsilon. Okay. Let's now see if we can get to this by starting with the assumption that x is an upper bound, which is not the supremum. I'm going to tell the reader that that's the route we're taking, so we will show the contrapositive. Suppose that y less than x is the supremum of A. All right, so x is an upper bound, but it's not the supremum. Out there, there is a supremum because of the supremum property. Let's name that y. And we know that it must be strictly less than x because it's the least upper bound. Okay, and now it's like I have to come up with this special epsilon. And how do we do that? Well, imagine how x and y are situated next to or relative to each other on the number line. We have, a over here. We have x, and I'm now saying that the set supremum is y, which is strictly to the left of x. So then it's like I need some kind of width, some measurement epsilon. We're going to slide to the left of x by this amount epsilon. Any epsilon that slides us within this gap between y and x would work. You could actually go all the way down to y, but what I often like to do, just because I like to have little margins around me, is cut distances in half. So that's what I'm going to do. You're welcome to pick a slightly different epsilon if you like. So I'm going to say let epsilon naught, meaning epsilon subscript 0, be x minus y divided by 2. What can we now do with that? Well, let's see what it looks like if I take x and subtract epsilon off of it. Sorry, the special epsilon. Then x minus this choice of epsilon that we have made is going to be x minus x over 2 plus y over 2. It's going to be, let me just write that out, x minus x over 2 plus y over 2. And that is actually x plus y over 2. That's this midpoint here between x and y, and that is greater than y. Therefore, this number being bigger than y is also an upper bound because y is the least upper bound. So x minus this choice we made is also an upper bound. Therefore, every element from the set A is less than or equal to that number by definition of upper bound. So for all elements little a in the set big A is less than or equal to x minus the special epsilon that we designed. And that's really what we're trying to get to. It doesn't feel very satisfactory to me, but let me finish writing this as desired. Okay, so if x is not the supremum of A, then we can design an epsilon. So really here is the epsilon that we designed. It's the width that I just highlighted. We can design that choice of epsilon so that when we take it off of x, we end up with a number which is also an upper bound. And therefore, flipping this around, going back the original direction, if it's the case that for all epsilon greater than 0, including this one, you slide to the left of x by that amount, you pick up something from A, it must follow that x is the set supremum. All right, reading the two of these, I like the forwards direction better. Somehow the backwards direction doesn't land quite as well, but we did show this criterion. What I would like to do to wrap up this lesson is take this criterion and use it to do what I call algebra on suprema. So we're just going to take given sets and kind of modify them and deduce what the corresponding set suprema would have to be. Let's wrap up this video with these two exercises. So we want to imagine that A and B are two sets which are both bounded above. By the supremum property, we know that each of them has a supremum. What we are going to do is form two new sets. The first one we will call A plus B, and what that means is it's all of the terms that you could get by adding something from A to something from B. Then the second set that we will work with in a moment is like scaling A by some non-negative number C. We want to show that you can work out of this what the corresponding suprema for each of these two new constructions is. So notably, if you take two sets and do this sum procedure, the supremum of the new set exists, and it's the suprema of the original set added together. It's exactly what you think it would be. And similarly, given that C is non-negative, I can actually take it and just kind of pull it out in front of this sup process. Okay, we will prove both of these statements. Let's start with the first one. For any element, little a, I'm going to switch to x and y so that I don't have to keep using letters both in capital and lowercase form. For any x in A and y in B, the supremum of the set A plus the supremum of the set B must be greater than or equal to x plus y, because the sup of A is greater than x, greater than or equal to, and the sup of B is greater than or equal to y. So we just add together those two inequalities. This is true for any sum where the first term comes from A and the second term from B. Therefore, this A plus B construction produces a set which is bounded above. And here is one of the upper bounds. So thus, sup A plus sup B, the supremum of A plus the supremum of B, is an upper bound of A plus B. At this moment, all I can say is that this expression, the supremum of A plus the supremum of B, is greater than or equal to whatever the supremum of A plus B is. We want to show that we actually have equality. Let's go with contradiction. What if we didn't? So what if this inequality was strict? Just to let the reader know what's up, I will say, for the sake of contradiction, suppose that this was strict inequality. So the sup of A plus the sup of B was actually greater than the sup of the set A plus B. We are going to take a thought process kind of similar to the criterion that we just looked at. This number is bigger than this one, so there's some gap between them. I am going to let epsilon be half the distance of that gap, and here the division by 2 is actually necessary because I've got to kind of distribute to the two different sets here. You'll see that come out in the algebra in just a moment, so let me keep going. Let epsilon, a specific choice of epsilon I'm making, so I'm dropping a subscript on there just to tell myself this is not an arbitrary epsilon. It's something I'm defining to be this larger term minus the smaller term divided by 2. All right, I've given you a good choice of epsilon here to work with, something that would land us, say, right here. I would like for you to take a moment to see what you can do from here. So just experiment around with the set A, the set B, see if you can get to a contradiction here. So we want to contradict this inequality so that we can conclude that this should actually just be equality. Let's wrap this up, and what I'm going to use is that criterion that we just proved. So by the criterion, which you might have thought of from this notation here, there exists, I'm going to call it alpha in A and beta in B. So these are two elements from the sets A and B, such that alpha is greater than the sup of A minus this choice of epsilon. So that, again, is that criterion applied to the set A with its supremum. So here's the supremum of the set A. if I slide a little bit to the left, including by this special measurement that we just assigned, we'll pick up something from the set A, and that's what we're calling alpha here. And likewise, applying the criterion just to the set B, if I take the supremum of B and slide a little bit to the left, I have to pick something up, and that's what we're giving the name beta to. So we've got alpha and beta. They exist so that this inequality is satisfied. Let's add these two together. We have alpha plus beta on the left is greater than the sup of A. What I'm going to do is sup of A plus sup of B minus twice this special epsilon. But now look at this. If you bring this 2 over, so again, actually the division by 2 here was necessary. You can think about that, but if I bring this 2 over, we get the 2 epsilon. Normally I'd probably write out a little bit more, but I'm going to do this out loud because I'm out of room. But bring the 2 epsilon over, and then let me subtract that over. I get sup of A plus sup of B minus twice the epsilon equals sup of A plus B. Okay, so basically you can take this using this equality and replace this right-hand side with the sup of A plus B. And that's equality. Okay, so literally sup of A plus sup of B minus twice the special epsilon equals the sup of A plus B. That's a contradiction. I have now a sum of terms. So this alpha plus beta here is an element in the set A plus B, and it is greater than the supremum of that set. That doesn't make any sense. So we've arrived at a contradiction. Therefore, it can't be the case that we have strict equality. So let me just see if I can squeeze it here. So sup of A plus sup of B equals the sup of A plus B. So you can see how the criterion that we proved came into this computation. Take a moment to pause and see if you can wrap up this lesson with this exercise, and then I will come back and work through the details. First thing we should do is actually just handle the easy case, which is what if C is 0? Because notice here I said C is greater than or equal to 0. If C equals 0, then the supremum of the set CA is just the supremum of the single element set 0, which is 0 itself, which is equal to 0 times whatever the sup of A was. And we're done. Okay, so suppose that C is greater than 0 for the rest of the proof. The flow of the proof will follow the first exercise we did. So first let's show that CA is bounded above, and that's not hard to do because we know that A is bounded above. For any X in the set A, notice that, what am I trying to say? C sup of A is greater than or equal to CX. And that's just because sup of A is greater than or equal to X for any X in A, and I've multiplied both sides by this positive number C. So we preserve the inequality. X here was an arbitrary element from the set A, so that tells us that C sup A is an upper bound of the set CA. C sup of A is an upper bound of CA. Similar to the first exercise, we can now say that C sup A is greater than or equal to C, the sup of CA. Just like in the first exercise, let's imagine that this inequality was strict and apply the criterion for the sake of contradiction. Suppose suppose that C sup A is greater than the sup of CA, and you know what, I'm going to say that there's going to be a special value of epsilon, but I'm not going to write down yet what it is. Let's see if we can work it out in just a moment. So it's like, you're going to do this, but let's see what algebra is necessary over here on the right-hand side. So then, okay, what did we do last time? We defined the special epsilon, and then we went back to the original set and applied the criterion to the original set. So by the criterion, there exists an alpha in A so that alpha is greater than the sup of A minus the special value of epsilon. There's no C in this inequality. So this is just a statement about the set A and applying the criterion to that set, saying as soon as we slide to the left of the supremum of A, we've got to pick up something from the set A. We need to bring this into our discussion here of the scaled version of A. And let's do that by just taking this and multiplying through by C. Maybe I'll do that right here. C times alpha is greater than C times the supremum of A minus C times epsilon naught. And we preserve the inequality because C is strictly positive. All right. Let's see if I can keep going. I'm not sure what this algebra is going to be yet, but maybe it will fall out in just a moment. So consequently, if I look at, let's see, what do we have here? I think what I should do is actually go ahead and see if I can write down epsilon now because of this. So if I solve for epsilon naught here, I would have C sup A minus, what do I want to bring over? Well, C alpha, but that alpha is really specific. I think what I want to have here is going to be sup of CA. So I'm working this out on the spot and then divide by C. Okay, I had to pause for a second and work it out, but yeah, this is going to work out. Let's now take this C epsilon naught here and replace it with this expression. So I'll leave the left-hand side as it is. C alpha is greater than C times the supremum of A minus C times epsilon naught. So if I brought C over, I would have C times the special value of epsilon. So let's negate this. Minus C times the sup of A minus the sup of CA like this. And now look what happens. These cancel and we're left with sup of C times A. Okay. Just like before, I have a contradiction because on the right-hand side, I have the supremum of the scaled set C times A. And on the left-hand side, I'm saying I found an element of that form, C times alpha, where alpha comes from A, which is larger than the set supremum. That makes no sense because the set supremum is an upper bound. So we've arrived at a contradiction. Okay, sorry, I had to hesitate there because I thought, oh, I'll just work this out on the spot. And then I got a little turned around here, but it did check out at the end. The flow of this proof was very similar to the flow of the first one. So what I think you should do now is perhaps see if you can walk away for 30 minutes and then maybe prove these again. Also, you can come up with other kinds of statements here. Maybe the first modification that comes to mind is, what if C was negative? What would you be able to say? And if C is negative, you might see some sort of interchange happening between a suprema for one set and an infima for another. That might pair up well with an exercise on rephrasing that criterion that we had for suprema in terms of the set infima. So that's something else that I would like for you to do is come up with a criterion for a set infimum. I'll wrap this up here though. Thank you for your attention.